First problem, and this a common problem you might find in linear algebra, involves having this vector and an unknown resulting into another vector. We call this vector an ordered 4 tuple. So that's just important to note that that's what we call such a vector. And here we're just simply solving for an unknown. So just employ what you've been some of your foundational mathematics in finding out this unknown. So basically our first step is step 1 would be to isolate 2x. So we do this by taking this particular vector to the other side. So we would have 2x equals to this first vector minus this, because it has come to the other side. 5, 9, minus 6, 8, minus 4, minus 3, 1, 7. So this would be, we would have to work this out, whereby just imagine it to be 5 minus the first one, 5 minus 4, 9 minus 3, and then negative 6 minus 1, and then the last one 8 minus 7. So therefore we would get the final result as 1. This would be 12. This would be negative 7, and this would be 1. And then finally we would simplify for x, which is simply dividing by 2, and then all the constituents of this divided by 2, and we would find x, the unknown, to be a half, 6 minus 7 and a half, and a half. So basically that would be how you would solve such an equation. And in linear algebra we often work with the vectors just to understand transformations in the space, whether 3D, 4D, even 2D. Basically these are important aspects, and once we are able to just be comfortable with this aspect, we can understand why we are doing such a calculation. So in the next segment I'm just going to show you why exactly we just did this calculation and how relevant it shall be in your AI and machine learning journey. Thank you. So why should we care about such a math problem? Associativity makes computations reliable. So in vector spaces, like the one we've just done, such operations guarantee no matter how we group these terms, the result remains the same. And if that is the same, it means we definitely, have consistent outcomes. Moving on, in AI, when dealing with high dimensional data, images, embeddings, weight matrices, the consistency is so essential for reproducibility of results across different computational orders. Without this associativity, distributed computation, such as splitting across GPUs, CPUs, will yield inconsistent results depending on how partial sums are grouped. Moving on, basically neural networks depend on vector space structures. So every layer in a neural network applies linear transformations, which are basically matrix multiplications, dot products, and convolutions. So associativity of addition and multiplication ensures that things behave predictably. This is very critical because training involves billions of such operations. So if associativity didn't hold, gradients and outputs could drift, making optimization impossible. When we talk about distributed and parallel training, basically in machine learning, you have very large data sets that are split into batches and trained across multiple nodes. Gradients update each gradient updates from each node are then added together. So associativity ensures that no matter the order in which gradients are aggregated, the final update to the model parameters is the same. This allows scalability, parallelization, which is why modern AI models can basically train huge clusters. We're going to talk about stability in numerical methods. So optimization algorithms like SGD, Adams, etc. They depend on repeated vectors and matrix additions. Associativity guarantees that consistent updates and helps prevent guarantees consistent updates and helps to prevent error accumulation due to arbitrary grouping in floating point operations. Even though computers use approximate arithmetic, the theoretical backbone comes from these algebraic guarantees. So then the representation of learning and embeddings. Every layer in a neural network applies linear transformations, which is basically the matrix multiplications. So yeah, we'll just end there and go to the next problem. These five basically the representation, the distributions, and just ensuring that data remains consistent is very important in this particular discussion, and hence why it was very important for us to basically be able to do the previous equation and then move towards understanding its real life applications. So another problem that you'll find in the book is around testing complex numbers and specifically testing the associativity of addition. So we have this problem here, and we're being asked to basically show that show the associativity of addition. So the first step of just doing such a problem is basically we're just proving. We're having these parts of mathematics that we have to prove. So this first step, step one, involves writing the complex numbers in standard form. So by doing this, we'll be able to more or less expand the equation and be able to more or less prove this. So we have alpha into A and BI, beta into C and DI, and lambda into E plus Fi. So, and whereby A, B, C, D, E, and F are this. Okay, so that's the first step. Expand this so that we have these representations of the unknowns, and then when we go to step two, we compute first the left hand side. So opening these up and basically having these equations in their simplified format. So basically we have lambda here plus beta plus lambda, which when we open this up would be a plus bi plus c plus di plus e plus fi. Okay. Once we've expanded this, or rather we will then expand it by putting we'll simplify this by putting I on the outside. Okay, so the final result would be a plus c plus e plus b plus d plus f. Okay, we just simply took a, put it here, took c, put it here, put e here, and then the ones which had I as their coefficient, put I on the outside, and then b plus d plus f. So this we've computed the left hand side. So the step 3, the final step before we show this proof, involves computing the right hand side, and basically that would be alpha plus beta plus lambda, and that would give us this a plus bi plus c plus di plus e plus fi. If you notice, we can begin to see that we would end up with the same on this side as well, b plus d plus f plus I. So notice a here, c here, e here, and then the rest which have the coefficient as I ending up here. So what do we notice? This and this are the same. Then that means once we compare, we can say we can then conclude by saying that the addition of complex numbers is associative, as we have just done a simple proof to show this. And this I will just delve into why this is very important in the field of AI and machine learning. So why should you care about the second problem? Again, very important also to understand. AI requires something called feature representation. So in AI and machine learning, data points which refer to images, words, patients in healthcare, etc., are represented in vectors of different tuple lengths. So here our ordered 4 tuple is just a feature vector in 4 dimensions. So it could be, if you think of an application, it could be a patient record, which is age, weight, blood pressure, cholesterol. It could also be an image patch represented by 4 extracted features, or a word embedding in the low dimensional, which could be 4 numbers. So solving an equation like this is basically finding the unknown vector x which satisfies a transformation constraint. So that being said, we also have linear transformations. So the problem was essentially v plus 2x equals to w. So where v and w are a 4 vector tuple. This is the type of operation that is done in every neural network layer, applying, scaling, addition, and solving for unknown parameters. So in machine learning training, we repeatedly adjust weights x so that when combined with inputs, we approximate the outputs. We also use this kind of problem to understand optimization and solving systems. Machine learning is about solving equations in high dimensions. So you can think of like your 4D equation is a very simple case whereby we're solving for x in a system of equations. In reality, AI models deal with millions of dimensions. So understanding this helps to, push to the next level. Geometric interpretation. So vectors in 4-tuple are points in 4D space. So basically solving for x is like finding the unknown point after scaling and shifting, which lands on an exact target point. So in machine learning, this is how we fit models and move parameters, points in in high dimensions until predictions align with labels. Then lastly, we have applications in practice, and this basically involves computer vision. Think of it robotics. How do computers actually see without sight? But a 4-tuple could represent the RGBA color vector of a pixel. Adjusting it is like image transformation. We have natural language processing, NLP, which is a 4-dimensional embedding, which is a toy version of the 300 D word embeddings actually used. We also have recommender systems. A user profile can be a feature vector. Solving equations like this helps to estimate missing preferences. I also have neural network training, which at each iteration, equations like your R4-tuple example appear inside the weight updates. Yeah. So basically, this is how those two equations tie back to deep aspects of AI and machine learning. And these are just two examples that we are solving. We have developed a very elaborate PDF with all the relevant linear algebra topics to AI, machine learning, computer science, any hobbyist who wants to get into these artificial intelligence systems. We've developed a great PDF that is basically able to give you the rundown and help you understand the deeper concepts, tying the equations to real life scenarios and applications that you can use. So follow the link in the description, like and subscribe. The book is on Gumroad for $25, and it's available for all topics in linear algebra. And you can take your understanding to a deeper level. You can beat those classes. You can get to have a strong foundation. Thank you so much for joining, and see you in the next video.